Hi, my name is Lena, and I'll be presenting my paper, Learning from Mistakes, Combining Ontologies via Self-Training for Dialogue Generation. We know that creating NLG data-to-text datasets is labor-intensive and time-consuming, but new attributes are constantly being added to databases. We want to be able to reuse and combine data from existing ontologies and their associated training data to create new utterances. Here is an example. Let's say we have one ontology and training data called NYC, and we want to be able to generate combined utterances which have attributes from not only NYC, but also another data set and ontology, E2E. We would then create a meaning representation, or MR, with attributes from both sources that we dub combined or COM. While these data sets do have some unique attributes, they also have some in common, like the two in this example, which are shown in orange. That the names for area and location are different is not important since they realize the same information and mapping can trivially fix this. NYC has a dialogue act that E2E does not have, and 3 attributes that are not in E2E's ontology. These are represented in red. E2E also has 3 attributes in blue in this example that are not used in NYC's ontology. When we combine the ontologies together, we can create new MRs that have attributes from both original ontologies. In row 3, we can see that there are all 3 types of attributes in the combined test MR. We then want to be able to generate an utterance that contains attributes from both ontologies, especially the attributes unique to a single ontology, which are represented in red and blue. An example utterance is in the last column of the 3rd row. Our paper makes 3 main contributions: the definition of a generation task for generating from unseen MRs that combine attributes from 2 datasets with different ontologies, systematic experiment on methods for conditioning NLG models, and a novel self-training method that learns from the model's mistakes. First, I will go over ontology merging a bit more. There is first one source of data, NYC, with its ontology. Our example has 2 types of dialogue acts and 7 attributes. We then have a second source of data, E2E, with a different ontology, which has 1 dialogue act and 8 attributes. Because they are in the same domain, there are 4 attributes that overlap. We can then combine the ontologies together after merging and relabeling attributes to create 1 large ontology with 2 dialogue acts and 11 attributes. Our data comes from 2 sources in the restaurant domain, the E2E generation challenge and the NYC dataset. The training data is balanced over the 2 datasets, resulting in a dataset of about 77,000. We then manually create a test set with 3,040 MRs, where every MR combines attributes from each dataset, and half the test instances utilize the recommend dialogue act. The lengths of the MRs are normally distributed between 3 to 10 attributes. Also, since this is a new ontology, there are no gold standard references to compare to in test, since the whole point is this data doesn't exist and we had to create this test set ourselves. Our model architecture is represented on the right. It is a standard RNN encoder-decoder model with 3 types of side constraints as model supervision, also called conditioning, 2 which are input to the encoder and 1 to the decoder to represent which source the data comes from. Here is a more in-depth look at the model supervision. First, we have the NOSUP, where there is no additional source supervision. Then we have the adder supervision, where the source information is appended to every attribute. Next, we have the bool supervision, where the source information is in a new attribute. And finally, we have the guide supervision, where the source information is inserted directly into the decoder. I will now describe our text-to-meaning semantic extractor. We create this for 2 reasons. First, we don't have gold references, making automatic evaluation using methods such as blue impossible, so we need to be able to determine the semantics in the utterance automatically for evaluation. Also, we need to retrofit MRs for self-training. I will go over our self-training regime in more detail later. Our method is a rule-based automatic aligner that tags each output utterance with the attributes and values it realizes. We have an example on the right. We can see that the original MR and the output don't match. While there are a good number of attributes that are properly realized, represented in orange, there is an extra value not in the original MR, represented in green, and 4 attributes in the MR that are not in the output. We can modify the original MR to create an MR using the text-to-MR extractor that removes the attributes from the MR which are not in the output and inserts the attributes in the output that are not in the MR to create a new and accurate MR. And a similar approach for automatic evaluation has been used in previous work. We have 3 types of evaluation metrics. First, we have the slot error rate. This calculates the semantic error by using the text-to-meaning semantic extractor to determine the number of the 4 types of semantic errors which can be present in utterances and normalizing them by the number of slots in the input MR. We also have the perfect percentage evaluation metric, which is the percentage of outputs that perfectly match the input MR. And finally, we have the human evaluation on naturalness, coherence, and grammaticality. Here are our model's initial results. We can see from these results overall that this is quite a challenging task because none of these results are very good. In fact, the perfect percentage is below 6% for all models. Of the 4 models, Adder has the most perfect utterances, though NOSUP and Boole also do comparable. Guide does surprisingly poorly, and we will therefore not include it in the rest of the experiments. We also perform human evaluation to determine if these results are at all natural, coherent, or grammatical. We can see that the human evaluation, which is only done on semantically perfect utterances and therefore must have some combining of ontologies, is quite good, indicating that we do have utterances we can potentially work with. So how can we make this work? We decided to try self-training. We need a couple of things to attempt self-training. We need perfect outputs, so the MR matches the utterance that combine attributes from both sources to add back into training. And we need outputs that are natural, coherent, and grammatical. From the human evaluation, we know that we have the latter, but our initial model results indicated that we have very few perfect outputs. But this can be resolved using the text-to-meaning semantic extractor to retrofit corrected MRs. As we showed earlier, by taking an original MR and an output, we can generate a fixed MR, which is shown here as the text-to-MR, that has the corrected attributes and values, and therefore can be considered perfect. But we don't just need perfect outputs, we need ones that combine attributes from both sources. We define a new metric, source blending, that counts the number of combined outputs. This graph unpacks these previous results according to the length of MR and source blending results. We can see that there is a significant number of source blended utterances, much more than the 5.5% of perfect utterances in our initial best model. We can also see that the Boole model has the most source blended utterances, making it a potential best option as the model supervision for self-training. We also need to remember that half of our test set includes recommendation dialogue acts. So we also need a model that can produce recommendations. Boole not only has the most source blended utterances, but also has the most source blended utterances with the recommend dialogue act. This cements our decision to continue with the Boole model for self-training. For our self-training experiments, we start with the 77,000 training examples and then add back in 1,405 retrofit MR NLG outputs from the Boole model. We experiment with 2 types of self-training regimes, S-repeat, which keeps repetitions and adds them back into self-training, and S-unique, which only adds unique outputs back into self-training. Here are our self-training results over 10 iterations, where the perfect percentage goes up considerably, reaching 82.9% for S-repeat, a 77.4% absolute improvement over our initial results. Our slot error rate also drops to close to 0 with our S-repeat model. Since the COM test set was used during self-training, we construct a new test set using the same procedure as before, called COM2, and test it on the final iteration of our models across different MR lengths. We can see that while these results vary across MR length, they are comparable to COM, and we therefore know that the trained model generalizes to new test sets. Here we compare the results of S-repeat, our best model, with the results of Boole, the initial model for self-training, to highlight the difference from before and after self-training. While perfect percentage at longer MR lengths are 0% for our initial model, they are over 50% for every MR length after self-training. Here are some example outputs from the self-trained model, where we can see a number of aggregation methods are used to combine attributes from both sources, not just concatenating the separate sentences. For example, in the first row, we can see the recommend dialog act from NYC is combined in the same sentence with the E2E attributes, family friendly, and eat type. In the second row, the NYC and E2E attributes are joined using a with operator, and in row 3, there is a single sentence with 4 attributes. The NYC attribute is preceded and followed by the E2E attribute with the reverse in the last row. In conclusion, these are the first experiments on training an NLG for an extended domain ontology by reusing existing within domain training data. We show that this task is surprisingly adversarial and that self-training methods results in high quality, natural, coherent, and grammatical outputs with high semantic accuracy. In future work, we plan to generalize to combine 2 distinct domains and possibly improve self-training with additional reference list evaluation metrics. Thanks.